This is Physics 2120, Lecture 19, and today we're going to talk about inductance. So before we begin, we need to discuss some terminology. We're going to use EMF and current when they are caused by batteries or other power sources. We're going to use induced EMF and induced current when they're caused by changing magnetic fields. And when dealing with problems in electromagnetism, it's very important to distinguish between those two different situations. Now, if I just have a basic circuit, a battery and a resistor and a switch to turn it on, when the switch is first closed, the current does not immediately reach its maximum value. And we can use Faraday's law to describe why it takes a while to start. As the current increases with time, the magnetic flux through that current loop due to this current also increases with time. The corresponding flux due to this current then also increases. This increasing flux then creates an induced EMF in the circuit. The direction of that induced EMF is such that it would cause an induced current in the loop, which would establish a magnetic field opposing the change in the original magnetic field. So the direction of the induced EMF is opposite the direction of the EMF of the battery. And the result is that there's a gradual increase in the current until it gets to its final equilibrium value. This effect is called self-inductance because the changing flux through the circuit and the resultant induced EMF arise from the circuit itself. The EMF, E sub L, is called a self-induced EMF. So if I look at a coil and try to understand this EMF, in A, there's a current in the coil that produces a magnetic field directed towards the left. If the current increases, the increasing flux creates an induced EMF with a polarity as shown in the picture that opposes the current. The polarity of the induced EMF reverses if the current decreases. An induced EMF is always proportional to the time rate of change of the current, or E is minus L di dt. L is the constant of proportionality, and we call that the inductance of a coil, and its value is going to depend on the geometry of the coil and physical characteristics of the wires. So we know that the inductance is minus L di dt. We also know that that EMF is minus N d flux dt. So comparing the two, a closely spaced coil of N turns carrying current I has an inductance of N flux over I, or minus E over di dt. The inductance is a measure of the opposition to a change in current. The SI unit of inductance is the Henry, and 1 Henry is a volt-second per amp, and it's named after Joseph Henry, pictured there on the right. So, what about a solenoid? What's the inductance of a solenoid? Well, let's assume I have a uniformly wound solenoid having N turns and length L. We're going to assume L is much greater than the radius of the solenoid, so it's longer than it is around. We've already determined that the interior magnetic field of the solenoid is mu naught little n I, which is mu naught the number of turns per unit length times I. The magnetic flux through each turn then, flux is B times A, is mu naught NA I over L. Therefore, the inductance is N times flux over I is mu naught N squared A over L. So, the inductance of the coil depends on the number of turns, the cross-sectional area, and the length. It depends on the geometry of the coil. Now, we can have an inductor in a circuit, and it's going to do certain things to a circuit. So the first thing we're going to look at is an RL circuit, or a resistor-inductor circuit. The circuit symbol for an inductor looks like a coiled wire, or a solenoid. We assume the self-inductance of the rest of the circuit is going to be negligible compared to the circuit element, the inductor that we put in. However, even without a coil, any circuit does have some self-inductance. That inductance always results in a back EMF. Therefore, the inductor in the circuit opposes changes in current in that circuit. So, an RL circuit is a power source, a resistor, and an inductor. When the switch is closed, the current begins to increase. At the same time, a back EMF is induced in the inductor that opposes the original increasing current. We can apply Kirchhoff's loop rule to this circuit, and gives us, if we go around the circuit this way, E minus IR, and the EMF over the inductor is L di dt. This is a differential equation that we would need to solve to figure out what the current is as a function of time. So E minus IR minus L di dt is equal to 0. Or L di dt is equal to E minus IR. We can divide by E minus IR and multiply by dt. And then we're going to put the minus sign on the dt, and so it switches signs over here. Now we can integrate both sides of this equation. And L is a constant, it comes out of the integral, so di over IR minus epsilon is equal to minus the integral of dt. Well, minus the integral of dt is easy, that's just going to be t. In order to integrate this side, we need to do a u substitution. We'll let u be IR minus epsilon. So du is going to be r di. When I is equal to 0, u is minus epsilon. When I is equal to some final value, u is IR minus epsilon. So we're going to put that into our integral. We end up with a du over u, which we know is a logarithmic function. We can multiply by r over L. Then take the exponential of both sides, and we get IR minus E over negative E is E to the minus RT over L. We can simplify this a little bit more, multiply both sides by minus E, bring this E over to the other side, and we get IR is equal to E times 1 minus the exponential of RT over L, or I as a function of time is the battery voltage over the resistance times 1 minus E to the minus RT over L. So the current changes exponentially. The inductor affects the current exponentially. The current does not instantly increase to its final equilibrium value. If there's no inductor, the exponential term goes to 0 and the current instantaneously reaches its maximum value, as we would expect. The expression for current can also be expressed in terms of a time constant tau of the circuit, where the current is E over R times 1 minus E to the minus T over tau, where tau is L over R. Physically, tau is the time required for the current to reach 63% of its maximum value. So if I were to graph what this looks like, the equilibrium value of the current is E over R, just what we would expect, and is reached as t approaches infinity. So the current initially increases very rapidly, and then gradually it begins to approach the equilibrium value. The time rate of change of current is a maximum at t equals 0, and it falls off exponentially as t approaches infinity. In general, the time rate of change of current is E over L times E to the minus T over tau. Now I can also discharge an LC circuit, where maybe I have this switch closed, and I get it going, and I get this equilibrium value, and then I take the battery out of it. Now even without the battery in that, this inductor does not like a change in current, so it's going to continue to push current through the resistor. And we can also use Kirchhoff's rules to solve this problem. We would see that this time the current decreases exponentially. So we can go back to our equation that we got from Kirchhoff's laws, And we can multiply each term by I. And so this is going to give us energy terms. So IE, that's the rate at which energy is being supplied by the battery. And I squared R is the rate at which energy is being delivered to the resistor. And then LI di dt must be the rate at which energy is being stored in the magnetic field. So let's let U denote the energy stored in the inductor at any time. The rate at which energy is stored, du dt, is Li di dt. We can cancel out the dt on both sides, and if we do, we can integrate to find the total energy. So U is L times the integral of I di, or 1/2 Li squared. So, for example, for a solenoid, U is equal to 1/2 Li squared. That's 1/2 mu n squared Al, and I is B over mu naught n. We cancel things out, we get B squared over 2 mu naught times Al. And Al is the volume of the solenoid, so the energy density in an electric field was 1/2 epsilon naught E squared. In this case, it's 1/2 1 over mu naught B squared. The energy per unit volume inside the solenoid is B squared over 2 mu naught. This applies to any region where there's a magnetic field, not just a solenoid. It's analogous to the expression we got for the energy density. So let's look at an example problem, a coaxial cable. They're used in electronics to minimize outside interference in signal carriers. So first, what is the magnetic field in between? We know that the magnetic field in between is mu naught I enclosed over 2 pi r. I don't care about the field inside the wire, or out here I only care about what's going on in this, and we can use Ampere's law to figure out exactly what it is. Long straight wire. Barriers in the cable, such as a television or a cable signal. Current travels up the center wire and returns down the... So the flux through this area here is the integral of B dot dA. So that's going to be B, mu naught I over 2 pi r. And the A here is the length of the wire and a little thickness of it. So L is the flux over the magnetic field, or it's the flux over the current, so it's mu naught L over 2 pi times the natural log of B over A. Again, the self-inductance of this is purely a geometric property. There's some constants here, but it's the length of the wire and it's the inner and outer radii. So to figure out self-inductance, we figure out the flux through it, we divide by I, and that'll give us the self-inductance. Is dr. So the total energy then is 1/2 Li squared. So that's going to be mu naught L I squared over 4 pi times the natural log of B over A. We're going to integrate over R, so the mu naught I L over 2 pi comes out, and I end up with a dr over R, which is just going to give me a log of B over A. Outside shield. I want to calculate the self-inductance of a length L of the coaxial cable as an inner radii. Now, if I have two loops nearby, they can affect each other. The magnetic flux through the area enclosed by a circuit often varies with time because of time-varying current. So here I have two coils next to each other. And the current in coil 1 here sets up a magnetic field. And some of those magnetic field lines go through coil 2. Let's say coil 1 has a current I1 in N1 turns, and coil 2 has N2 turns. The mutual inductance, M12, of coil 2 with respect to coil 1 is the number of turns in 2 over the flux through 2 due to 1 over the current in 1. So mutual inductance depends on the geometry of both circuits and on their orientation with respect to each other. If current I1 varies in time, the EMF induced by coil 1 in coil 2 is, the EMF is minus N d flux dt, which is going to be minus M di1 dt. Of course, if the current in I2 is in coil 2, there's an so in mutual inductance, the EMF induced in one coil is always proportional to the rate at which the current in the other coil is changing. And the mutual inductance in one coil is equal to the mutual inductance in the other coil. In other words, M12 is the same as M21, and so we'll just call it M. And so the induced EMFs can be expressed as the EMF in coil 1 is M times the time rate of change of the current in coil 2, or vice versa. Mutual inductance going the other way, M21. And if current 2 varies with time, the EMF induced by coil 2 and coil 1. So wireless devices use this fact of mutual inductance. So many cordless devices use this. A coil is hooked up to some AC source, like a household power that's going to have the current changing back and forth. And the cordless device has another coil. When placed close to each other, the powered coil causes an induced EMF in the second, which we can then use to charge an internal battery in here. So let's say I have two solenoids, A and B. They're spaced close to each other. They share the same cylindrical axis. And they have 400 and 700 turns respectively. A current of 3.5 amps in coil A produces an average flux of 300 microwebers through each turn of A, and a flux of 90 microwebers through each turn of B. Calculate the mutual inductance of the two solenoids. What's the self-inductance of A? What EMF is induced in B when the current in A increases? So first we know the definition of mutual inductance is NB, flux through B due to A, divided by the current through A. We increases at a rate of half an amp per second. Is minus M21 di2 dt. It's exactly the same, only in just reversing the numbers from 1 to 2. It's in nearby circuits. And that process is known as mutual induction because it depends on the interaction of two circuits. Radius A and an outer radius values, we know there's 700 turns in B. The flux through B due to A is 90 microwebers. And the current in A is 3.5 amps. In B, we know the self-inductance of A is the number of turns in it times the flux through A over the current through A. So we work that out is 18 millihenries. Yes, B. So the flux through A is 400 turns. There's 300 microwebers due to the magnetic field. And we know that the EMF in B is minus M di dt in the coil, divided by 3.5 amps, so we get 34.3 millihenries. So that's going to be the 18 millihenries, and we know that di dt was 0.5 amps per second. So to review what we talked about today, we started about self-inductance, how any circuit loop, it takes a while for current to get to full value because the changing magnetic field inside the circuit loop causes an EMF that opposes that change. We also talked about inductors in a circuit, and we talked about mutual inductance. What if I have two currents loops next to each other, how they can affect each other. And we also spent some time talking about RL circuits. Second, and so we get 9 millivolts EMF induced in coil 2.